The service cannot be 200 amps and cannot be fed from a 200 amp 3-pole main circuit breaker. The National Electrical Code, NEC, requires that the service rating be based on the expected demand. This demand is calculated as follows: demand equals total connected load times demand factor. The demand factor considers the diversity of the load, meaning that not all loads will operate simultaneously. For commercial buildings, a demand factor of 0.75 is typically used for lighting and receptacles. Let's look at some calculations. Lighting demand equals 20 kV amps times 0.75, which equals 15 kV amps. Receptacle demand equals 50 kV amps times 0.75, which equals 37.5 kV amps. Motor demand equals 10 kV amps times 1.0. Motors have a demand factor of 1, which equals 10 kV amps. Total demand equals 15 kV amps plus 37.5 kV amps plus 10 kV amps, which equals 62.5 kV amps, which is 178 amps. A calculated demand is 62.5 kV amps, which is more than the 200 amp service proposed. Therefore, the service rating must be increased to accommodate the actual demand. A 250 amp service would be sufficient for this load, as it provides a safety margin and complies with NEC requirements. Determining the appropriate service size for a building involves several steps, and it's crucial to follow the guidelines set forth in the National Electrical Code, NEC, to ensure safety and compliance. Firstly, you need to identify all the connected loads. This means accounting for every electrical device or piece of equipment that will be drawing power from the service. This includes lighting, receptacles, motors, heating, ventilation, air conditioning, HVAC systems, and any other significant electrical loads. Secondly, for each of these loads, you must determine their volt-amp rating. This information is typically found on the equipment's nameplate. It specifies the amount of power the device consumes under normal operating conditions. Thirdly, it's important to understand the concept of demand factors. Not all electrical loads operate simultaneously at their maximum rated capacity. The demand factor is a multiplier less than or equal to 1.0 that is applied to the connected load to estimate the actual demand on the electrical system. This factor accounts for the diversity of the load, recognizing that different loads will be used at different times. Fourthly, the NEC provides guidance on appropriate demand factors for various types of loads. For example, lighting and receptacles in commercial buildings often have a demand factor of 0.75, reflecting the fact that not all lights and outlets will be in use at the same time. Motors, on the other hand, typically have a demand factor of 1.0, unless there's specific information indicating otherwise. Fifthly, once you have determined the volt-amp rating and demand factor for each load, you can calculate the demand for each load individually. This is done by multiplying the connected load in volt-amps by its corresponding demand factor. Sixthly, after calculating the demand for each individual load, you need to sum these demands to find the total demand on the electrical system. This total demand represents the estimated amount of power that the service must be capable of providing. Seventhly, with the total demand calculated, you can determine the minimum required service size. This is typically expressed in terms of amperage. To do this, divide the total demand in volt-amps by the service voltage. Remember to account for the number of phases, if applicable. For example, in a 3-phase system, you'll need to divide by the square root of 3, approximately 1.732. Eighthly, a calculated service size should be considered the minimum. It's often prudent to add a safety margin to account for future expansion or unexpected load increases. A common practice is to increase the calculated service size by 25%. Ninthly, the service equipment, including the main circuit breaker, conductors, and any other protective devices, must be rated to handle the calculated service size. It's essential to select equipment that is appropriately sized and rated for the intended application. Tenthly, it's important to consult the NEC for specific requirements and guidelines related to service sizing. The NEC provides detailed information on demand factors, conductor sizing, overcurrent protection, and other critical aspects of electrical installations. To reiterate, the NEC requires that the service rating be based on the expected demand, which is calculated as follows: demand equals total connected load times demand factor. The demand factor considers the diversity of the load, meaning that not all loads will operate simultaneously. For commercial buildings, a demand factor of 0.75 is typically used for lighting and receptacles. Now, let's review the initial example. Lighting demand equals 20 kV amps times 0.75, which equals 15 kV amps. Receptacle demand equals 50 kV amps times 0.75, which equals 37.5 kV amps. Motor demand equals 10 kV amps times 1.0 because motors have a demand factor of 1, which equals 10 kV amps. Total demand equals 15 kV amps plus 37.5 kV amps plus 10 kV amps, which equals 62.5 kV amps or 178 amps. The calculated demand of 62.5 kV amps is greater than what the 200 amp service is proposed. Therefore, the service rating must be increased to accommodate the actual demand. A 250 amp service would be sufficient for this load, as it provides a safety margin and complies with NEC requirements. When performing these calculations, it's important to adhere to the National Electrical Code (NEC) guidelines and best practices. The NEC provides specific requirements for service sizing, including demand factors for different types of loads, conductor sizing, overcurrent protection, and grounding. Consulting the NEC and engaging with qualified electrical professionals can help ensure that your electrical service is safe, reliable, and compliant. Service sizing is a critical aspect of electrical design and installation. By following the steps outlined and adhering to the NEC requirements, you can ensure that your electrical service is adequately sized to meet the demands of your building or facility. This promotes safety, prevents overloading, and ensures reliable operation of electrical equipment. Considering the different demand factors for lighting, receptacles, and motors is crucial for accurate service sizing. Lighting and receptacles often have demand factors less than 1.0 due to their intermittent usage. Motors, on the other hand, typically have a demand factor of 1.0, unless specific information indicates otherwise. Applying the appropriate demand factors to each type of load ensures that the service size is optimized for the actual demand. It's also essential to consider the voltage of the electrical system when sizing the service. The service voltage affects the current carrying capacity of the conductors and the rating of the overcurrent protection devices. Ensuring that the service voltage is properly matched to the loads and equipment is critical for safe and efficient operation. In addition to demand factors, it's important to consider other factors that can influence service sizing. These include the potential for future expansion, the presence of any large or unusual loads, and the specific requirements of the local utility company. Taking these factors into account can help ensure that the service size is adequate for the present and future needs of the facility. Ultimately, proper service sizing is essential for ensuring the safety, reliability, and compliance of electrical systems. By following the guidelines outlined in the NEC and engaging with qualified electrical professionals, you can ensure that your electrical service is adequately sized to meet the demands of your building or facility. This promotes a safe and efficient electrical environment for all occupants. For a 208-volt 3-phase 4-wire system, you would use the following formula to determine amperage amps equals kilovolt amps times 1000 divided by voltage divided by 1.732. For a 480-volt 3-phase 4-wire system, you would use the following formula to determine amperage amps equals kilovolt amps times 1000 divided by voltage divided by 1.732. For a 120-volt single-phase system, you would use the following formula to determine amperage amps equals volt amps divided by voltage. For a 240-volt single-phase system, you would use the following formula to determine amperage amps equals volt amps divided by voltage. It is important to note that these are simplified formulas and may need to be adjusted based on specific circumstances and local electrical codes. Always consult with a qualified electrician or electrical engineer for accurate calculations and safe electrical practices. Furthermore, remember to include a safety margin when sizing electrical components. It is generally recommended to select components with a capacity that exceeds the calculated load by at least 20%. This helps to prevent overheating and premature failure of the components, and it also provides some flexibility for future expansion of the electrical system. Also, always use appropriately sized conductors for the calculated load. The National Electrical Code, NEC, specifies the allowable ampacity of conductor based on their size, insulation type, and installation method. It is important to select conductors that are capable of safely carrying the calculated load current without exceeding their temperature rating. Overcurrent protection devices, such as circuit breakers and fuses, should be selected and installed to protect the conductors and equipment from overloads and short circuits. The overcurrent protection devices should be sized to trip at a current level that is below the ampacity of the conductors they are protecting. Grounding is an essential safety measure in electrical systems. It provides a low impedance path for fault currents to return to the source, which helps to trip overcurrent protection devices and prevent electrical shock hazards. All electrical equipment and enclosures should be properly grounded in accordance with the NEC. Regular inspections and maintenance are crucial for ensuring the continued safe and reliable operation of electrical systems. Inspection should be performed by qualified electricians or electrical engineers to identify any potential problems or hazards. Maintenance tasks such as tightening connections, replacing worn components, and testing overcurrent protection devices should be performed on a regular basis to prevent failures and ensure the long-term performance of the electrical system. The NEC is a comprehensive set of standards and guidelines for electrical installations. It is updated regularly to reflect the latest advancements in technology and safety practices. It is essential for electricians, electrical engineers, and other professionals involved in electrical work to stay up to date with the latest edition of the NEC and to follow its requirements closely. It's always best to consult with a qualified electrician or electrical engineer to determine the appropriate service size for a particular application. They can take into account all of the relevant factors and ensure that the electrical system is safe, reliable, and compliant with the NEC.